Water Digest. I invite Sri G. Ashok Kumar, Additional Secretary and Mission Director, National Water Mission, to kindly propose the opening address. Over to you, sir.
Good afternoon, everybody. Welcome to the 10th Water Tech Talk today. We had been holding this Water Tech Talk since October 2020, and it's been a great success. A lot of intellectual discussions have taken place here, and a lot of quality discussions have taken place here. We had earlier also senior professors from various colleges coming. We had Dr. Vishnu Kumar here from the NIH, from IAEA talking last time on isotope application in water resources. We had Dr. Ashwagosha Ganju, Director of SASC, speaking earlier. Dr. Nupur Bahadur, Fellow of the Water Treatment Technology R&D Division of Delhi. Dr. Indra Shekhar Sen, Assistant Professor, Department of Earth Science, IIT Kanpur. And also people from the industry side, Mr. Pinto from the India National Water Company, Israel. So we had Dr. Rajiv Sinhaji from IIT Kanpur and Dr. Pradeep from the IIT Chennai, Mr. Osjan Ekenjan from the IVL Swedish. So we have had a mix of people from the industry side as well as from the academic side, talk on exclusively on the water technology issues. Today also we have Dr. Deepak Kashyap, Professor of Civil Engineering IIT. In fact, he founded the Civil Engineering Department there and continued to teach there till and then he has taken a break on that. So he is from the IIT Kanpur, passed out in 1974 with his master's in hydraulics and water resources, and had been a very senior person in dealing with water. He had been interested with evaluating the performance of CWCs and NIS R&D departments. His research interests include groundwater modeling, planning, management, simulation, optimization, etc. He'll be going to talking to us on advancement of groundwater management practices in India. It's a very interesting topic because groundwater is a big elephant in the room. Not people have understood it, and probably we have been misusing it. And Catch the Rain campaign, which is the thing in campaign which is going on well in the country, launched by Honorable Prime Minister on March 22nd. It is the Jal Shakti Abhiyan Catch the Rain campaign. Also, is trying to address the groundwater issues because we found that the groundwater was getting depleted very fast, and many places are running very summer. But we have a lot of floods and overwater flowing all over the place when there's a severe rain. So, which means that and we also felt that the groundwater table has gone very drastically in many places, which requires of tankers. And not only that, many places have gone barren because of the extraction of groundwater. So groundwater is very important. Is very important. That's what we're going to focus on the Catch the Rain campaign. When PM said that catch the rain where it falls, when it falls. Basically, it is intended to ensure that the groundwater is replenished. More we draw from the underground water, groundwater goes down unless we keep on replenishing it. That is the need of the hour, and the campaign is also very relevant today, and hence the topic of thoughts on advancement of groundwater management practice in India is very relevant. We are one country where we extract more water than groundwater than US, China, and Mexico put together. Almost 55% of the groundwater extraction in the world is done in our country. We also use a lot of energy resources for pumping out the water, whether using the form of diesel or as well as electricity. So there is a very important need to address this groundwater issue, whether it is the issue related to water, or whether it is strategic important related to energy management, where more and more energy is being consumed for, whether it is the issue related to the type of agriculture pattern which we should handle. All these things are there. So this is a very interesting thought, because we also have to model it, because modeling is also very important. And I'm sure Dr. Kashyap would be talking about all these things in the speech. Dr. Kashyap, this is a very niche audience we have. We have people, actually a totally academic audience, where we look for people from institutions like IITs and theory and other places where water is taught as serious subject. So the thrust of the water tech talk is on technology and also the science related to water, whereas we have water talk which comes on every third Friday, where we bring in activists and people who are in the field looking after the conservation of water. That's basically a policy and administrative matters, and also related to activism on water. So this is a purely academic, highly technical things which we have, and we try to keep it. Welcome you for the talk, and you have 1 hour, 1.5 hours to speak on, and then there will be a question and answer session, and questions, and then take the questions. And in case we are not able to complete the time answering, they will take it up in the return form and then send it to you, so that you can answer it us, and we'll send back to the questioner. So all the options are available, and we have about 2 hours total time frame with us for you to speak, or then question and answer session. Thanks a lot, Dr.
Thank you, Shri Ashokji, for the kind introduction. Thank you. Am I audible well enough?
Yes, very much.
Okay, thank you. So I'm first of all thankful to the National Water Commission, and specifically Shri Ashokji and Shri Tejdeep Singh Ji for this introduction, for this invitation for the water talk. And this water talk is occurring at a very crucial moment of my life. That is, my career is culminating. I've had a career in groundwater which started way back around 1977 and has been continuing. And just recently, as I mentioned in my title, I retired from the visiting professorship of IIT Ropar. I retired from IIT Roorkee as there I was professor and head of civil engineering department in 2016, and was then invited by director of IIT Ropar to join the place and set up a new civil engineering department. So I've been here for last 5 years, and now this tenure has come to an end. So it's a kind of culmination of my professional career. Although I do have some offers, but there won't be any substantive involvements as such. So as I said, since I'm kind of culminating in my career, I take a liberty of a little bit of sermonizing and issuing homilies. I've been fortunate enough to have been invited for several lectures throughout my career, but this one, as I said, is special because of the reason that I stated. So if I recall back, my involvement with groundwater and specifically groundwater modeling started in late 70s, around 1977-8, when under the guidance of stalwarts in the area, Professor Satish Chandra, I was inducted into groundwater modeling. And I also had good fortune of having a very meaningful interaction with another stalwart of groundwater modeling, that is Ramsden, Dr. Irwin Ramsden. So they got me started. And then in 1977, remember we are talking of how many, 40 years back, groundwater modeling was in a very nascent stage. It was more of a philosophical concept. There was a thought that using some numerical tools, we can project the aquifer response to various pumping or recharge strategies. But there was no really hands-on study going on at that time. So I would like to say that we at Roorkee, with Professor Satish Chandra at the helm of affairs, we were the first to initiate hands-on groundwater modeling studies in India. And this was certainly helped in a very large way by Central Groundwater Board, which sponsored a very prestigious project to us that was modeling of induced recharge in Ganga Basin. And simultaneously, we also got several projects from the UP Groundwater Department. So that got us started. And we really was in hands-on mode very early in my career. And then, at that time, ModFlow was not there. In fact, it came much, much later. So we wrote our own codes, which do practically everything and maybe a little more what ModFlow does. But the catch was our codes were very, very user unfriendly. They could be used only by a handful, few of us who wrote those codes. So although now I use ModFlow as well, but I still keep reverting back to my own codes. I feel more at home with my codes rather than ModFlow. So this is the brief, summary of the career of mine in groundwater. And then I had another good opportunity of serving the Groundwater Estimation Committee, the GC committee, which set up the norms for groundwater planning in India and considered to be almost Bible. So with this now, I just share my presentation. Is it visible?
No, sir.
Is it visible, please? Hello?
No, sir.
Okay.
Not yet. Not yet.
Okay, just a moment. Share. Okay. Just a moment. Yeah, actually, at here in our institute, we use Google Meet, so I'm more comfortable. Okay, sorry, just a moment. Yeah, right. So thanks for the patience. Is it visible now? Hello?
Yes, sir.
Yes, sir.
Yeah, okay, thank you. So as I said, I'm going to take liberty of sermonizing a little bit. I thought with my long experience in the domain, I have a broad perspective. I was involved in evolving the current practices, and then I have been fortunate enough to have been involved in several projects like Sobarn Rekha irrigation projects, Sardar Sarovar, Upper Krishna, and so on. So, I'm going to project today some thoughts on how the practices of groundwater planning and management in India can move on. We already have quite robust practices which are serving the purpose very well. But now it is also a time to move on and imbibe additional capabilities and address additional issues. So, to get started, groundwater planning management essentially involves two broad steps. All groundwater primarily it owes, it owes its existence to the recharge from rainfall. So the first step towards management of groundwater is to estimate the recharge. And then second, which is very crucial, all the recharge which is received by an aquifer is not really utilizable. There are certain technical requirements as well as logistical compulsions. So some part of this recharge has to be allowed to flow out to hydraulically connected drains or to flow out to sea in case of coastal aquifers. And then there's going to be an inevitable evapotranspiration. So these lateral outflows, which may be outflow to the hydraulically connected streams or even to sea, plus the evapotranspiration, they combinedly form what we can call as losses. So the utilizable resource is essentially recharge minus. So these two steps now can be performed in a variety of ways with varying rigor. We can have very kind of crude estimates, which can be quick, to very elaborate and more reliable estimates. So we will first look at the first part of the practice, that is the recharge estimation. So, recharge is primarily a process, if I may just, recharge essentially, occurs as flow through the unsaturated zone. So we have rainfall occurring over the ground. Some part of this rainfall would be running off as surface runoff to the streams. The balance would be infiltrating. And then some part of the infiltration would be evapotranspired. Some part may be used up in building up the soil moisture deficit in the unsat zone, and the balance goes as recharge to the water table, which ultimately provides the resource. A fraction of recharge is deemed to be resource. So recharge process is actually, it is governed by the flow through unsaturated zone. So the most direct way of estimating the recharge would be to model the flow through unsaturated zone, or what we can call as modeling of unsaturated flow. Now, this is a predictive tool in the sense for any given infiltration at the ground surface and for the lower boundary conditions and for the given soil characteristics and the evapotranspiration, we can estimate recharge. Now we have a very robust differential equation governing flow through unsat zone known as Richards equation, whose solution can provide estimate of recharge. Now the second method, which is a kind of indirect or implicit method, is really to look at the signatures of the recharge on the water table. So that is primarily what is called as a water balance of the saturated zone. So if I again go to the next picture over here, see this recharge is received over here, over the water table. And this zone below the water table is the saturated zone. So instead of following the mechanism, the real mechanism which leads to recharge, we look at what the recharge does to the water table, or the impact of recharge on the water table, which would be visible as signatures. Like there may be a rise of water table, and consequently there may be an increased lateral outflow or decreased lateral inflows. So we look at the signatures of the recharge on the water table. And this essentially is accomplished by performing the water balance over a historical period. That means previous periods whose data are available to us. So there is a marked difference between the estimates obtained by the two approaches, whereas the first approach can give us estimate of recharge corresponding to any given forcing function, which is infiltration at the top. The second approach basically gives us the recharge as it occurred during the historical years, right? And from there, we can draw up some broad conclusion about the recharge characteristic of that particular basin. So our Indian practice or the GEC practice is actually the second, the historical water balance of saturated zone. That means we look at how the water table rises as a consequence of recharge during the monsoon period. So we already talked about this modeling of flow through unsaturated zone. So we have a plant which is evapotranspiring, and then the balance goes as recharge to the water table. Now we have a well-known equation for this zone. But there are certain inherent difficulties in solving Richard's equation, primarily the nonlinearity. The Richard's equation is highly nonlinear, so the algorithms are far more demanding. And secondly, more importantly, in our context, the data requirements. This modeling requires characteristics of the soil in the unsat zone, in the unsaturated zone, the variability of hydraulic conductivity and the head with the soil moisture. Now, in our practice so far, we have not started monitoring the parameters of this unsaturated zone. So due to this reason, this approach remains largely unutilized at the practice level in India, though at some project level, some specific projects, including a few that were done by us, this approach also has been used. So the second is the water balance approach. So if we consider the saturated zone, again, if I go back to this diagram, all this zone, all this aquifer below the water table, that can be termed as saturated zone because there all the pore space in the soil is filled up with water. So if we conceptually show this to be the saturated zone, then there are several inflows into the saturated zone and several outflows. So we write a very basic equation of hydraulics. That means all the inflows minus all the outflows is equal to the change of storage. So this is known as continuity equation, and it is invoked with different levels of rigor, right from being an algebraic equation as it is here to a differential equation, right? So now the first two terms are on the left hand side where my cursor is moving right now. These two represent the inflows. So inflows are divided in two parts. First, we can call as I prime. So I prime are the inflows into the saturated zone other than rainfall recharge, right? And the second term here represents the rainfall recharge. It is expressed as a fraction generally called recharge coefficient multiplied by the precipitation occurring over the ground surface. So this I prime plus alpha times P is the total inflow, and this is the total outflow. Now, this, one component of inflow is already there, alpha times P. Other components included in I prime can be, return flow from irrigation, artificial recharge, influent seepage, and so on. All right. And similarly, the outflow, the primary component of outflow is groundwater withdrawal, but there could be some outflow in the form of evapotranspiration from saturated zone. Now, most of the evapotranspiration, especially from agricultural plants, takes place from the unsaturated zone. But the deep seat, the tall trees whose roots go way below the water table, they would be evapotranspiring from the saturated zone also. So that evapotranspiration plus the pumpage plus other components of outflow, for example, effluent seepage, they would all be included in this term outflow. And on the right hand side, I'm writing the change of storage. So if we apply this equation over a monsoon period, then there is certain rise of water table and multiplied by areal extent of the basin or the reckoning area multiplied by the specific yield. So this is the change of storage. So the practice in India is to estimate all components of inflow other than rainfall recharge, that means I prime, and the outflow, and the average rise of water table during a rainy season. All these are computed using historical data of water table elevation at the beginning of a rainy season, at the end of a rainy season, and the pumping and other hydrological activities which go on during that rainy season under reckoning. So the general approach is that, as I said, we estimate everything other than alpha times P. So I prime O delta H. A is known, that is the area, and SY is known, maybe from pumping tests or other field tests. So we estimate alpha. So alpha and precipitation during that period, rainfall during that period is also known. The average rainfall can be obtained by, say, Thiessen's polygons over the study area. So we estimate alpha. So alpha is what? This is the fraction of rainfall which is going as recharge to the water table. So this is a very useful fraction and generally called as rainfall recharge coefficient, or sometimes for the sake of brevity, it is also called just recharge coefficient. So this is assumed to be a basin parameter, right? We presume that for a given basin, alpha as obtained from this water balance equation is a stationary parameter. Stationary parameter essentially means it remains time invariant. Although, see, just to get the perspective right, we would have obtained alpha over historical years, let us say last 5-10 years. So we can presume that this alpha is going to be valid under the coming years, in the coming year. Although, as we shall see, so far, this assumption has been working well, but now with the changing climate, this becomes a huge catch. So we are going to visit this issue in a short while. So as I said, this is very questionable assumption under changing climate. But right now, we presume that this alpha stays on as it is. Right. So now the next question is, how do we estimate the utilizable part of, if I go back, yeah. the utilizable resource. This is equal to the recharge minus losses. Losses are logistical requirement and also technical requirements. Like for example, we have to let some storage, groundwater storage flow into river as base flow. So that is necessary for the health of rivers in the lean flow period when there is no surface runoff. And similarly, in coastal aquifers, we have to let some water flow out to the sea for restricting the seawater intrusion. Right. So now the question is, how do we determine this utilizable resource or what we can call as a utilizable part of the recharge, which can be considered as resource, groundwater resource. So here again, there are two approaches with quite varying rigor. The first approach is rather subjective with the baseline rigor. We presume that this recharge, this resource, groundwater resource, is some fraction multiplied by recharge, and this theta is less than 1. So it could be say 60% or 70% or 80%, right? We keep it less than the recharge because we have to let some water flow out to sea or to rivers, and then there is some inevitable evapotranspiration. So this approach is part of Indian practice. It is serving well with some hydrological and hydrogeological judgment and based upon past data and past applications of GEC norms, a fair enough value to theta can be assigned. But again, this may work under many conditions, but under certain conditions, it may require a further firming up using models, basically. Now, second is, what I just said, the modeling approach. So in this, we have models, the saturated flow model, which can project the aquifer response to different levels of theta. For example, if we presume that theta is 0.2, right? So, or 0.2 is too low, let us say 0.6. So with 60% of recharge being considered as a resource. So if we pump that much of water, how is the aquifer going to behave? So this can be projected using aquifer response modeling. And then we can also compute the corresponding state variables like the depth to water table, lateral outflow, static storage, and seawater intrusion, taking cue from what I just said, and so on. So we can immediately see the advantage of second approach over the first approach. First approach is a kind of black box. We assign some holy number to theta and then let it go, based upon our judgment. But here we can be more objective in our assignments, and we can actually project that if we consider this to be our resource, how the aquifer and the state variables are going to behave. Now, Indian practice. Now, I've already been, broadly giving cues to that. So primarily based upon the GEC norms, considered holy in India, if I may use that term. And the norms have generally served the purpose very well, although they have been there for long. And sorry for the typo, though there are a few issues, they are serving the purpose well. There are some issues, and in fact, some of those issues I'm going to raise today, and also I'm going to suggest how the GEC norms can be enhanced to accommodate the issues that I'm talking of. Now, here again in Indian practice, modeling has been imbibed in the practice. Now, our Central Groundwater Board and also the state groundwater departments, almost all of them have modeling cells. But those modeling studies are generally, by and large, conducted in a standalone mode. And the modeling is still not being used for the mainstream resource estimation. The mainstream resource estimation is still based upon the resource being taken as a rather arbitrary fraction of recharge. So, we have expertise available in the Central Groundwater Board, other groundwater department, and more importantly, we have now very extremely user-friendly software and packages. I would here just raise a caution. The packages are user-friendly, but sometimes they are over user-friendly to the extent that they can be easily misused or used inappropriately by the practitioners. So it has to be an educated use of those packages. Right. So I'm going to still talk of the Indian practice. So the water balance, approach that we have talked essentially gives us the historical recharge coefficient, and it is fairly science-based. The recharge estimation is fairly science-based. The continuity equation is essentially the law of conservation of mass. But the catch is this subjective stipulation of this development factor or utilization factor. Now here again, a lot of thought has been given. Now theta is kept less than 1. That means we presume that only a part of the recharge is the resource. Now this has a very big advantage. This means that we are letting some part of the recharge to outflow to sea, outflow to river. So this means that we are not letting the river water to enter into the aquifer. And this is a huge measure for groundwater protection, quality protection, because river water is invariably of poorer quality than the groundwater. In fact, unfortunately, in India, groundwater remains only the good quality water for drinking and other purposes. So it is very essential that we protect it. And very happily, our GC norms promote the protection, although indirectly, not stating as such, but keeping theta less than 1. This means we are avoiding the induced recharge or the flow of river water into the aquifer. But there are some, flaws or some deficits. There's no provision for the static storage for drought management. We all know that droughts, not only in India, but worldwide, are managed by groundwater development during a failed monsoon year. But ironically, the drought management does not feature in the GEC norms. And similarly, we have a large tract of coastal aquifer. We have a huge coastline and very potent aquifer aligned all through. And there is no thought to that, the seawater intrusion. We have to let some groundwater to flow into the sea to restrict the seawater intrusion. Now that is not kept in the GEC norms. So the norms are fine, they are serving well, but they need to be enhanced, and that enhanced would be essentially by a synergic joining of the GEC norms with modeling. And we fortunately have already built up good expertise of modeling in our practice fraternity. So it is not very difficult to catch up. All right, so I'm going to discuss some of the issues now, having dealt with the country and what are the issues. So I'm going to now talk of some specific issues. So the first is the climate change. Now, climate change cannot be wished away. We are already seeing the change of rainfall pattern. This means the change of rainfall intensities. Now, we all know that groundwater recharge is dependent not only upon the total monsoon rainfall, but it is very, very closely dependent upon the time distribution of the total rainfall during the monsoon period. That means the rainfall intensities. Now, it is well known through various studies which have been conducted for Indian basins that the rainfall intensities are going to increase in the monsoon period. So this is going to have a huge implication on the recharge. That means all the wisdom which has been gathered over the years using the historical data, that may suddenly become invalid. For example, the recharge coefficient, they may serve the purpose well enough under the pre-climate change condition, but under climate change condition, those recharge coefficients are not available and are not, may not work, would not be credible. So this means that we need now predictive tools for recharge estimation. That means we have to go back to the primary tool, the primary tool for recharge estimation, that is modeling of the Unsat flow. Now we have, like, we have good packages and software for saturated flow, or what we call as groundwater flow modeling. Similarly, we have now very good state-of-art package for Unsat flow, that is Hydrus. And already I'm very happy to see many of the groundwater departments are already experimenting with that software, the Hydrus. But to implement that, we have to start collecting the soil data also. See, so far all our groundwater exploration has been oriented towards the saturated zone. That means we are periodically monitoring the water table elevations, the piezometric head, and we are conducting pumping tests for estimating the parameters of saturated zone. So all this exploration is essentially oriented towards saturated zone. So now we would be compelled very soon, we are already in that state actually, to use Unsat flow modeling for estimation of recharge. So for that, we very quickly should start gathering or exploring the soils and estimating the soil parameters, or what are known as K theta and H theta characteristics. And we have no historical data are not going to be valid for the changed climate. So this is the due diligence which is required. That means switching from, see, if you recall, I said the current practice in India for estimation of recharge is to do the lumped water balance of the saturated zone. So from that, we have to now very quickly move on to the modeling of Unsat flow, which is not difficult. We have the software, but of course, we have to get the soil characteristics. We have to start exploring the soil characteristics as regularly as we explore the characteristics of saturated zone. Now, the second issue, which is actually very important and which unfortunately has been ignored so far, not even finding much mention as far as I can recall, in the GEC write-up. That is the drought management. The droughts are managed by groundwater development during a failed monsoon year. So, if we want the groundwater to provide us some subsistence level water during the drought period, then we have to make sure that it has adequate static storage. That means the storage which is available at the beginning of a monsoon period. So that storage is available for the monsoon period. If the monsoon does come, that storage would play a role. But if the monsoon fails, then the storage, the static storage, would have a much larger role to play. It would provide us the subsistence level pumpage during the drought period. So it's already being done, but we have to practice it now. The drought hydrogeology, dealing with the planning of groundwater development to mitigate droughts. And we have to do the drought analysis. That means the frequency of droughts, the static storage need, and then incorporation of the static storage in the planning process. That means in the process for the estimation of resource. So here I have drawn a relatively simplistic picture of how the drought is managed by the groundwater development. So, here H represents the water table elevation. So this is the water table elevation hydrograph during normal rainfall years. This is deterministic approach. That means corresponding to the average rainfall. But of course, in the stochastic approach, it may show some variation around the mean cycle. But the average cycle may be like this. So now see, this is the beginning of the next monsoon. See, this is the monsoon period when the water table rises. And this is the non-monsoon period. The water table rises because of the rainfall recharge. And this is the non-monsoon period when the water table declines because the pumpage exceeds the recharge. There is practically no recharge in the non-monsoon period. So the pumpage well exceeds the recharge during non-monsoon period, so it declines. So if the next year were a normal monsoon year, it again would have risen and then fallen. But now there is no rainfall. It's a failed rainfall year. So this storage, which is occurring at the beginning of what would have been a rainfall period, but now it is not a rainfall period. It coincides with the rainfall period, but there is no rainfall. So this storage is very important. You see that if this storage is not adequate, then the groundwater resource cannot be used for drought mitigation. So now what happens I'm considering a few drought years, say 3 drought years, to take a very extreme scenario. So during these drought years, the groundwater development pumpage takes place to meet the minimal irrigation requirement, or municipal requirement. So there would be a decline. So the requirement is that at the end of drought years, we still should have some storage, leftover static storage, which is required for accommodating the screen of the well. For the wells to function, the screen of the well as well as the drawdown in the well, that has to be accommodated within this differential elevation. So the minimum it should go is this unutilizable static storage. So what does it mean? That means we must design or plan our static storage that the static storage, the residual static storage available at the end of drought years is adequate for well functionality. So this means that this static storage is very important. It's an important state variable, and which can be computed using the aquifer response model or the saturated flow model, which I talked of. So now let us say after this unfortunate, say, drought, a set of drought years, 3 years, we have normal years, normal monsoon year. So the water table would start rising. This is how it would rise. And after some number of years, like here, 1, 2, 3, 4 years in this case, it reaches back the pre-drought state. Now, this also is very important. We must so plan our static storage that such that the normalcy is restored before the onset of the next drought, right? Because see, it would be very awkward if the next drought starts here itself. For example, at this point where I'm placing my cursor, this is the beginning of the monsoon year, monsoon part of the year. All right, let us say there's no monsoon rainfall here. So what will happen? What will happen? Okay, sorry. If yeah, here, if for example, if the monsoon fails, then it would start declining, and now it would very quickly use up all the static storage, and the wells will become dysfunctional. That means the groundwater can no longer be used for drought mitigation. So we have to so plan that this period for the restoration of normalcy is shorter than the expected interval between two droughts. Now, the expected interval between the two droughts can be estimated by doing frequency analysis of the droughts. So this is the broad planning policy. Now, so what this basically means is we have to plan for adequate static storage. And in terms of resource assessment, it means leaving out some part of the resource unutilized for management of possible drought. See, it is like an insurance. We spend money for insurance, which helps if there is a calamity. If there is no calamity, it can be considered as an unutilized resource, but that is essential. So if we need an insurance against drought, then we have to let some fraction of the resource unutilized during normal monsoon years. This is the policy point, which can be quantified through groundwater modeling, as I shall show subsequently. So model assimilation, model assisted planning for drought mitigation. So we have to check the drought preparedness corresponding to the prevailing pumping pattern. So we do the model assisted projection of post-drought saturated thickness for a trial value of theta. And if I may go back, I'm talking of this depth, the post-drought depth of saturated thickness. This is the lower impervious layer, and this is the water table elevation at the completion of the drought period. So if this is adequate, that means we are already prepared for drought mitigation. But if there is a deficit in D, then we have to moderate the value of theta. Theta, remember, is the fraction of rainfall which is to be utilized, which is to be considered as a resource. So then actually this can be done through model assisted and linking it to an optimizer, the simulation model linked with an optimizer can provide us an optimal value of theta, which would be just adequate to meet the drought mitigation requirements. So I'm giving a small example here. In fact, this is an MTech thesis which was done by a student of mine at IIT Roorkee in 2015. This is planning of agricultural groundwater development for drought management mitigation. This is in region 5 of Sardar Sarovar Command, bounded by Shady River and Narmada Canal and Sabarmati River over here. So this is the area. And the planning parameters here was, looking at the well functionality in that area. A value of 15 meter was assigned in consultation with the practicing engineers from the region. This is the stipulation that we want to arrive at such a groundwater development pattern which leads to a post-drought saturated thickness of 15 meters, right? And then in that area, the major use of groundwater is for irrigation, agriculture. So we considered only agricultural groundwater development. And groundwater pumpage is linked to the cropping pattern and the irrigation demands of the crop areas. So then, checking the drought preparedness for the existing cropping pattern, first of all. Existing cropping pattern. So this is the existing cropping pattern. Of course, this was obtained some few years back, several years back. So the idea was to illustrate the procedure rather than addressing the on-ground problem, because the full data were not available. Right. So this is the cropping pattern which was used and which typically represents the typical cropping pattern. And this is the pre and post drought water table elevation fields above the mean sea level. And because the models, the groundwater flow models essentially provide the water table elevations above any chosen datum. So here the datum is mean sea level, so about 10 meters. But our planning state variable is the depth to water table. So the field of water table depth was obtained by subtracting the water table elevation from the ground elevation. And this is the post-drought saturated thickness field. What does it mean? That means if we go for this cropping pattern and provide all the irrigation requirements of this cropping pattern through groundwater development, then the water table elevation is going to stabilize at these levels and at this depth. So this is the post-drought saturated thickness. And here, the minimum saturated thickness, which is actually coming somewhere here in small areas, is 12 meters, which is less than 50 meters. We, right in the beginning, stipulated that we require a saturated thickness of 15 meters for the mitigation of drought in that area. So this means that theta, remember, theta has to be moderated. And in this specific case, theta is relatable to the crop areas. That means the cropping pattern has to be modified. So the cropping pattern was optimized. The cropping pattern was optimized so that the minimum saturated thickness at the end of the drought period increases from 12 meters to 15 meters, right? So this is the optimal cropping pattern. And in the next slide, I'm presenting the depth to water table. No, sorry, the saturated thickness. So the minimum saturated thickness, as was expected, does come out to be 15 meters. So this way, we can, moderate our pumpage through the moderation of the cropping pattern so that the water table elevation at the end of drought period is still adequate for wells to function, right? So that is that cropping pattern. All right, so, so this now, can be very easily incorporated in the GEC norms. All we have to do is, we can assign some value to theta. Maybe in the drought prone area, we assign a little lower value than what we may normally stipulate. And then using the model of that area, groundwater flow model, we determine this D, the saturated thickness, for a trial value of theta. And if this D is found to be okay, let us say in the first trial itself, in that illustration, if we had found D to be 15 meters or more than 15 meters, then whatever theta we are suggesting is fine. But if it is found to be less than the required D, then theta has to be reduced. And again, we do our model runs and compute the value of D. So iteratively, we can arrive at such value of theta, which gives us the required D. Or this can be actually, as was done in this illustration, which I just showed, it can be done by linking the flow model with an optimizer. All right, now another is the planning in coastal aquifers. Now, as I already mentioned, outflow to sea is necessary for controlling seawater intrusion. So this means that for a permissible seawater intrusion, the outflow requirement has to be met. And this outflow requirement can be assessed by appropriate models. The seawater intrusion models. Like there are the simplest model for seawater intrusion is the Gibbon-Herzberg equation, which says that the depth of the freshwater interface below the mean sea level at any location is simply 40 times the height of water table elevation above the mean sea level at the same location. So this means that if you reduce the water table elevation by 1 meter, it means that the interface between the salt water and fresh water, that means the salt water would move up by 40 meters. So you can see that it is a very sensitive dependence. So we have to determine the required outflow to sea for maintaining a given level of seawater intrusion. And then this outflow need, remember, can be incorporated in that. If I go to the previous slide. Yeah, this can be incorporated in this term O. This O can be the pumpage from the coastal aquifer and also the required outflow to sea for maintaining the required level of seawater intrusion. So you can see that it is very easy to assimilate all these finer points of planning in the GC norms. So the outflow need, which is assessed by the seawater intrusion model, I already talked of Gibbon-Herzberg equation, which is the simplest model. Then we have a more rigorous model. Now NIH at Roorkee, they have a very considerable expertise in seawater intrusion. In fact, there I am very proud to say that Dr. Anupama Sharma there, who's the prime mover behind such models there. She was my student at IIT Roorkee. She has since then, of course, moved on and made a niche for herself. So this outflow need now can be incorporated in the GC norms. Okay, so I'm just giving here, the drill which can be gone through, stipulate permissible extent of seawater intrusion, compute the corresponding outflow, and compute the resource, and model the resulting seawater intrusion, and check if it is within the limits, and if it is not, revise theta and repeat this drill. So this is the procedure, but you can see at the core of this would be the GC norms. It would all revolve around GC norms. The other is groundwater quality protection. Now, this is very important part of groundwater resource estimation and management. See, so far, generally, when we talk of groundwater resource, we typically talk of the quantity. How many million cubic meters of water are going to be available for groundwater development? But if all that water which is coming in is of poor water quality, then it's not a resource anymore. The resource is not just the quantity, it is quality also. So it is very important that the quality aspect is incorporated. And as I already mentioned, implicitly or indirectly, it is already incorporated. How? As I already elaborated, by keeping theta, that groundwater resource factor, less than 1. That means GC norms say don't use all the recharge, don't pump out all the recharge. Let some of the recharge flow out to the rivers. What does it mean hydraulically? That means the gradient is from aquifer to the water, aquifer to the river. So that means the river, this stops, this preempts the entry of river water, which is a huge, huge relief from the water quality viewpoint. But there are additional threats to the groundwater quality. That is the leachates from within the aquifer. So, or additional pumpage. If, for example, if we go for additional pumpage in any area, and the water table declines below the river stage, then the river water would enter into the aquifer and may deteriorate the groundwater quality. So this means, the first step towards installing a good regimen for groundwater quality protection, in addition to what is already there, the regimen in the context of quantity, we have to develop solute transport models. These are more elaborate than the flow models, like mod flow, that primarily is a flow model, although now they have incorporated solute transport segments, but a full-blown solute transport model is far more elaborate. So these models can be used for projecting the impact of any pumpage or recharge on water quality, right? So these models now need to be brought into the practice. But to be able to see, for installing these models, we first need models and the training. We have already intellectually very advanced people in the domains of Central Groundwater Board and even state groundwater departments, but that has to be further strengthened. More and equally importantly, we need data. See, as I said, our data monitoring is oriented towards quantity and saturated zone, monitoring water table elevations and piezometric and conducting pumping tests. But in addition to that, now I think our departments have also to start monitoring water quality parameters. quite on the same lines as water table elevation. So in fact, the same monitoring points can be used for monitoring the water quality. And this has to be done on the routine basis. That means periodically, say every month or 4 times a year, or every month, or pre-monsoon or post-monsoon, depending upon the requirements of that particular area. So then this is a relatively new area, a new area of hydrogeology, that is forensic hydrogeology. Now you can immediately connect forensic is something like policing, conducting police surveillance on hydrogeology. That means keeping a track on what is going on in the aquifers. Now, we have very stringent regulations for the disposal of leachate from industry or municipal or irrigation systems into the groundwater. But unfortunately, those norms are not always adhered to. There are many camouflaged or clandestine disposal of pollutants into the groundwater system. Now, using the tools of forensic hydrogeology, we can identify such hidden or camouflaged pollution sources and take suitable action. Some industry, for example, on paper, they may be declaring that they are treating their effluents and only the treated effluents are being disposed of into the groundwater, but their treatment may not be of the required level. They may be saving money on treatment. So this would have signatures on the concentration of the water table elevation, of the groundwater in the unconfined aquifer. So now in last several years, we have got several models which permit such forensic numeric action. This is a numerical policing or computer policing. So, just to give, this is generally the differential equation governing two-dimensional solute transport in an aquifer. And here, this is the source. This is the source. This is the pollution source. And C is the concentration. And these dxx, dyy, and r and phi, these are the parameters. B is the thickness. And C is the concentration, which is a function of x and y. So if we have historical data of concentration, then we can estimate W. This is the major deviation from the routine solute transport modeling. In the routine solute transport modeling, for a given W, that means for a given leachate characteristic, and for the given parameters, we can project the concentrations. But in the inverse problem, for the given concentrations, we estimate W, the source. So this is an inverse problem. So solving the differential equation for the concentration fields repeatedly with varying source characteristics, and then identifying such source characteristics that reproduce the observed concentration fields most closely. That means basically we are solving that solute transport model, or conducting the solute transport modeling for iteratively varying values of W until the computed concentration field matches close enough with the observed concentration field. And this, iteration can either be done subjectively or it could be done through an optimizer. So here I'm going to present a study which was done by another PhD student of mine, Jyoti Chaube, in 2017. So this relates to identification of pollution sources in this area, Yamuna Krishna interbasin, lying in the western UP, very close to Roorkee. I used to consider this as my backyard basin there. So this is the area. So we had water table data and also the concentration data, water and the concentration data. Yeah, that's right. So bounded by river Yamuna and river Krishna. So we did this kind of study here. We solved this differential equation iteratively until the computed concentration field matched optimally with the observed concentration field. See, optimal matching means that we can never truly reproduce the observed concentration field, but as closely as possible. So these are the, these are the sources which have been identified. 4 sources were identified. And these are the leachates, the leachate intensity in those 4 sources. So spatial distribution of local sources at a discrete time, 2005. And then some field checks were made, and it was found that indeed there, at these locations, there are, these are the disposal sites. And then, as I said, we arrive at such, values of these W's or leachate intensities so that our model computed concentration field matches closest possible with the observed concentration field. And this is what it is. This is the observed concentration field. You can see. And here, this is the closest reproduction. It's fairly close, although departures are there. You can see that this is more because we are presuming those pollution sources to be geometrical. That is why these contours are also coming as geometrical. All right, so with this, I complete my presentation. Basically, on some issues, this is not an exhaustive list. There are several other issues too, but these are very important issues in my view and can be very easily addressed within the framework of GC by a little bit of tweaking and innovation, and broadly, in all cases, modeling the systems. Now, models, see, when I started, models used to be rather mysterious, and people thought that it's some kind of intellectual, one group of people even thought that it is some kind of intellectual fraud being played by academicians. But now we have come a long way. And the other school of thought at that time was that, I'm talking of late 70s, one school of thought is that it is a fraud being played by academicians. The other viewpoint was that it is panacea, it can solve all problems. But now we know it cannot solve problem. Modeling is not solving problem. Modeling is just knowing if you do this, this is what is going to happen. So it can evaluate our interventions. With the help of models, we can evaluate the intervention. And it is certainly not a fraud being played by the intellectual. We have come a long way since the era I'm talking of late 70s. Now we have a much more clear understanding of models and much better access to the models. So it is time that these are included in the practice of planning and resource estimation and management. All right, so with this, I come to the end of my talk. I thank you all for your time and patient listening. Thank you. So yeah, I'm going to stop sharing and we can discuss any questions. Yes.
Thanks,
please.
Professor Kashyap, for a wonderful presentation.
Hello.
Arun,
Thank
please go
you.
ahead.
Yeah, thank you, Ashok sir. Thank you. Yeah, actually, I can't hear. Are there some questions? Please, I'll be very glad to take questions. In fact, if there are no questions, I would feel let down.
Thank you so much, Dr. Kashyap, and it was wonderful hearing from you. There were so many, nice things which you spoke about, and there are already a lot of questions which have come to us through chat. And for all those who are joining us for the first time, I would like to quickly share with you that we are starting with the question answer session, and on your screen there is a chat window. You can always type your query there, or you can also raise your hand. We have an option of raising hand, so you may please raise your hand, and my team will unmute you. You can introduce yourself and then put forward your query. Okay, so we are officially open for the Q&A session. Can we take some query?
I request Dr. Dharamve Thareja, you may please ask your query.
Well, it was very, very informative, and with my knowledge of
Actually, Dr. Thareja, I can't hear you very well. Can you get closer to your mic or maybe speak a little louder?
is it am I audible now?
Yeah, now it is better. Yeah, it's better. Yes.
Okay. I must comment that with the surface water background, I could learn a lot from your presentation on groundwater, and the way, in a lucid way you presented, it was very, very absorbing kind.
Thank you.
I keep thinking that you said that concern about the climate change. Isn't
Yes.
it now we have reasonably, may not be as long as rainfall data, but we have a reasonable data on climate change and its impact on the groundwater too. Should we not be able to come to some reasonable conclusions and concerns?
Yes, yes, right. Very, very nice question, Dr. Reja, and thanks for your compliments. Always good to have educated listeners. Right. So, yes, you're right. The climate change is already a reality. In fact, my student at IIT Roorkee, he conducted a climate change projection for the same area, Krishna, Indian. And another of my student at IIT Roper, he has projected the rainfall patterns for this Satluj Beas region of Punjab. Now, see, one major change, and in the context of groundwater, one major change which is occurring is the increase of rainfall intensities. Now, this means that the water would, the rains would be occurring in a very intense fashion and then would be running off with the lesser opportunity time for infiltration, hence the recharge. So the apprehension is that it may lead to a reduction of the recharge, although the total monsoon rainfall may increase. But because of the increased intensities, the recharge component of the infiltration may actually fall down. And to model this, we need to model the Unsat flow. There, the forcing function to be introduced at the top, at the ground surface, would be these projected intensities. And this partly it has been taken up, though not in the full-blown way, by the students whom I talked of, and they have been able to estimate recharge, yeah, in a slightly moderated way, but a more, concerted, research is required. Again, I may point out, Dr. Reja, you already know it, that most of the climate change studies which have been conducted in India and overseas, they just project the hydrometeorological variables. That means the rainfall, temperature, minimum temperature, maximum temperature, and just stop there. In fact, when I started, I couldn't find any study on the impact of climate change on groundwater. So groundwater is affected through, the change of rainfall pattern. And if we want to estimate the recharge with the varying intensities of rainfall at the ground surface, then a lot of effort in the direction of Unsat flow modeling is required, which has yet to start in the full-blown way.
Can I ask something related to this?
Yes, please. Yes, please.
Because now that surface water reservoirs are kind of a thing of a past, it's not being built, and rather they are shrinking by way of sedimentation. And then we have to rely more and more in times to come on the groundwater resource.
Exactly.
Do you see there is some kind of an interconnectivity between the aquifers and some kind of utilizing it in a sequence in a way that you are able to tide over in times to come the droughts?
Yeah, can you just repeat the last part of your question? I couldn't. You said connect between. You talked of some connect between
the aquifers, so that like some of the surface reservoirs can be utilized in interconnected way if they are on the same basin.
Yes, that's right. Right.
Like
Yeah,
to tide over the drought, particularly when drought is there in some reaches and you have reservoirs kept at some locations. Is there a way to have, one way could be that you pump it and put it on the river and let it flow down. But is there anything like, because once you pump it, then it can be picked up on the way also. Like, is there a way that you have a deep-seated, some kind of interlinkage possibility?
Yeah, that's right. I can see your point. Pumping and letting it into river may not be efficient in my view. Pumping and using it locally. See, that is the advantage of groundwater. Groundwater is not a storage device, but it is also a transmission device. So wherever water is, because aquifers, at least in the alluvium part and even in the weathered zone, they are fairly spatially extensive. So water should be pumped during the drought year at the point of usage so as to minimize the losses. The other point which is very relevant, which you said, is whether this groundwater resource during the drought period can be used in conjunction with the surface reservoirs, which may have been only partly filled up because of the drought. So yes, it is possible to plan conjunctive use of the waters in the surface reservoir as well as in the groundwater. Although the study which I presented there, we presumed that due to the failed monsoon, the surface reservoirs are empty. And it is only the groundwater reservoir which is available for the mitigation. But if it is known that the surface reservoirs would also have some, that means if it is a partial drought, so if they do receive some inflows, then the two can be conjunctively used. That is what I think I could, if I gathered the sense of your question correctly.
No, I was thinking that if groundwater reservoir is located somewhere else.
Dr. Dharamveerji, I'm sorry to say I'll cut you here. Maybe we can take these queries separately with Dr. Kashyap. And there are a couple of more questions which I would like to put forward by other participants as well. So there is Ms. Ritu Thakur is wanting to know if both the climate change and water balance study relies on historical approaches, why climate change becomes an issue in water balance method of recharge estimation.
Yeah, okay, good question. See, yeah, right. We even for climate projection, we do use some historical data of rainfall, but that is primarily just to validate the models of rainfall projection. But just to get set the perspective right, while doing the lump water balance of the saturated zone aimed at estimating recharge, we take the historical water table elevations, which have been affected by the historical recharge. And historical recharge pattern may be markedly different from the recharge pattern under changed climate. So the parameters or the recharge figures that we get from the water balance of historical period would apply only to historical period. If there is no climate change, then we can presume that the traits of those historical periods are stationary on an average sense, and it can be used for projection. But if there is a severe change, then, for example, that recharge coefficient, if we arrive that as in a given basin, it is coming as 20%, 20% of rainfall going down as recharge. Now, under changing climate, it may come down to 15% or even 10% because of the modifying intensities. So that is what I meant, that all the wisdom gathered over the historical period is suddenly not available anymore, not valid anymore.
Another one, in the perspective of climate change only, in the context of climate change, can surface water storage into artificial recharge various intervention like borewell recharge or existing structure to increase groundwater in confined aquifer?
Okay, right. Yeah, this can be, yeah, provided we have adequate surface water availability. And if there is a time mismatch, that means when that surface water is available, we don't have the requirement. See, if there's a time match, then use it, use surface water then. But if there's a time mismatch, that means surface water is available when there is less demand, then of course it can be recharged into unconfined aquifer, or as you said, deep aquifers too. It can be done, but we have to again see, whenever we recharge, some part of that is going to be inevitably lost due to the boundary flows. So that can be modeled through numerical modeling. We can actually project what part of the recharge will be available for subsequent development. So a lot of care is required, in conducting recharge. Yes.
I hope, Mr. Shashikant Mehatre, your query, you got the answer for your query. Mr. Amit Singh is wanting to know how much can groundwater management contribute towards national water security? I think.
I think we now, the awareness of groundwater is very rampant. We all know groundwater has a huge role to play. It is already playing a huge role. The main advantage is you don't need reservoirs, you don't need canals, right? If we right here, groundwater reservoir, as I already mentioned, groundwater aquifer serves as storage system as well as the distribution system. And distribution right up to the farm level, farm of or home of the user. So it is far more efficient, and of course it has to be used in conjunction with surface water. Yes.
Okay. Mr. Paritosh Tyagi has put forward the query. He says that, is there a real threat to groundwater quality from the toilets being constructed on such a large scale?
Yeah, actually, yes, it is a very loaded, potent question. It's a very, see, no, I like to think that all those septic tanks and, all the related components of that would be adequately sealed through clay layers. There is a codal provision, I think, for adequate clay layering of those tanks, septic tanks and others. So if all care is taken, no, it may not affect. But if we are casual, and this may have been happening much before, these activities which you talked of. So there again, the effect would be most, even if it does, that means if we are casual in our designs, the effect would be most rampant on unconfined aquifer only, the water table, whereas the deeper aquifers may be relatively isolated. Unless we have multi-aquifer wells, I'm very concerned about that. I raised this question when wells were being drilled in Roorkee. What is happening? We have wells which are tapping all aquifers, including unconfined and the lower confined, the strainer. So that provides a direct circulation between the unconfined and the lower aquifer. So through those wells, multi-aquifer wells, the polluted water from unconfined aquifer could flow into confined aquifer or leaky confined aquifer. So that has to be avoided. That means there has to be adequate sealing. If the well is tapping the lower aquifer, it should be adequately sealed from the upper aquifer, which is a good practice being followed. But I've seen many careless contractors, careless or novice contractors violate this requirement.
So next, Mr. Uday Prasad. He is interested to know, sir, if these water management, groundwater management practices can help in improving drinking water quality as well.
Yeah, it would. Like, for example, yes, very, okay. Like, see, we are letting theta be less than 1, remember? So this means we are allowing for some losses. But it is quite possible that all these losses may go in evapotranspiration itself, and nothing may be left for outflow into the river. So under those conditions, it is possible that even if theta is less than 1, there may be some inflow of river water into the aquifer, which may be detrimental to the drinking water quality. So yes, if we go for these practices where we objectively determine through a simulation model the value of theta, and also go for that camouflaged modeling, which I talked of, the forensic. These would go a very, very long way in improving the quality for drinking as well as irrigation.
Mr. Alan Jensen wants to know that do we apply GIS in estimating recharge?
Yes. We estimate the okay, GIS. Okay. Yeah, GIS. Okay, right. I actually confused it with the GEC. Yeah, GIS is a good tool for data management, the spatial data management. Yes, GIS comes very handy in draw. You remember, if I said we have to compute the rise of average water table elevation during the monsoon season. That H is multiplied by area multiplied by specific yield, that is on the right hand side. Now for getting this, we have to draw the spatial contours of water table elevation at the beginning of the season and at the end of season. And GIS is very handy tool for drawing contours and for integrating the area over elevation for computing the groundwater storage. Yes, GIS is very, very, usefully employed. It is very potent tool for the GEC norms, as well as for, see, this GIS, if I may clarify further, is a good pre-modeling processor and the post-modeling processor, because the data availability is very different from the model input requirement. So this gap is bridged through GIS. Similarly, the output from the model may not be directly usable for management or planning. So there again, GIS processes the model output to yield the state variables which are more relevant to to the planning. For example, a model gives us water table elevation above a datum. Now that is not a planning tool, planning parameter. But if we GIS, if we feed the nodal values of water table elevation and also the ground elevation, it can give the contours of depth to water table, which is a very relevant state variable for planning. So yes, GIS has a huge, huge role to play.
So Mr. Prasad is wanting to know, how do we recharge the urban areas where 90% of, which is made up of 90% of concrete, how do we kind of recharge those areas for the rainwater runoff?
We have to have some sanctuaries, recharge sanctuaries. Some areas have to be left unpaved. There's no easy solution. If we can't over urbanize. Like in Delhi, for example, they have large forested areas, which acts as a recharge sanctuary. So similarly, those have to be installed, created, and then of course through wells, recharge through wells, but which is not as, in my view, as efficient as the natural recharge over unpaved areas through forest. For example, forest is a huge recharge, facilitator, because it does not let the runoff occur, and most of the water infiltrates and then recharges.
Whereas you also spoke about advocacy, and there is one question which I would like to put forward, which is by Mr. Ashok Dwivedi. He's keen to know that what kind of programs, awareness programs should be there as far as generating awareness about groundwater management is concerned.
You mean this program which you're talking of, is it for groundwater professionals or for common people?
So he's talking about common people, because I think that's what it means, because he's talking about generating awareness.
Yeah, I'm very glad this question has been raised. It's a very, very relevant question. Now see, I'll give you one example. Like, see, in this area where I'm currently located and where me and my student, we did a very elaborate study, groundwater flow modeling for the Satluj Byas region. Now, this is showing a declining trend, like most places. See, now what is happening as a consequence of declining of water table, more river water is induced into the aquifer. And also because of the increased unsat depth, there would be a larger leachate of the geological salts from the geological formation into the groundwater. So that means that the decline of water table is associated with the deterioration of water quality. Okay, and similarly, the decline of water table is also associated with the decrease of pumping capacity of the wells. See, for example, if a farmer has installed, say, 10 horsepower pump, now as the water table declines, the same horsepower pump would draw less discharge, right? And he has to pay more money. If actually government does charge for power, the power bill also would be higher. So, this kind of awareness has to be brought into the users. Say like farmers. In India, the major users for groundwater are the farmers. So farmers are very intelligent people. Like in Punjab, especially everywhere in Punjab, I'm talking of, what we have found that many farmers already know it. They may not know all the intricate processes and all, but they know that if they overdo their pumping, go for excessive pumpage, they are going to be sufferers in terms of their wells going dry and pumps being inefficient, and also the water quality deteriorating. So this awareness has to come in, right? And it is not very difficult to imbibe. In fact, we had a project with MIT, joint project with Massachusetts Institute of Technology, one of the leading institutes globally, and IIT Ropar, where we thought of linking the game theory with the flow modeling. Now, game theory is exactly this quantification of human psychology. Individual farmers think, one farmer may think, okay, I can pump more, but then not only he suffers, but also the people around him suffer. So game theory means that how much allowance he is going to make for others. This is a game that every person plays with others, and there is a quantification of that. It's a very well developed mathematical theory, which actually is very relevant for this kind of problems. So to answer, I am into this, so that's why I went to a little bit of elaboration. So to come back, yes, awareness among farmers that if they control their pumping, it is to their advantage. If they go for excessive pumpage, they are going to be sufferers. See, for the time being, okay, they may be able to irrigate more, but then in the next year, the crop yields are going to fall down because of the worsened water quality. So this kind of education, some farmers are already, they know it, but those who are not so knowledgeable, this kind of awareness is required.
Yes, sir. And I'm sure, sir, there must be a lot of programs which are already ongoing from government side where this awareness and basically considering that there should be a stronger governance structure when we talk about water issues exist. So many such programs are already being run.
Yeah, right. So the psyche of the, such programs have to address the psyche of the farmers.
Yes,
That in spite of free power, they should still not pump excessively. That's the thing.
Right, sir. Thank you, sir. And let
Thank
me
you.
congratulate you again because there are so many compliments coming in, and most of them are liking the session, and they have also complimented you for this wonderful and interesting and
Thank you.
informative session.
Thanks.
And I would now like to request Ashok sir for your concluding remarks. Ashok ji.
I can't hear. Is he online?
Ashok ji, I would like to have your remarks, sir. Okay, I think maybe some network issues. We are not able to unmute him. So no problem. I think we'll move ahead. And I now invite Mr. Sunil Kumar Arora, Advisor, National Water Mission, for his thank you note, as we are already approaching 5 o'clock and the Q&A ends here. And there are many more queries. And for all those whom we could not, your query, if we couldn't take here, you'll get all the replies on the website of National Water Mission. And I now request Mr. Sunil Kumar to kindly propose the thank you address.
Again, I think communication glitch.
Mr. Sunil Arora?
Okay, right. Nice there.
I think Mr. Sunil Arora is not available. I will be giving the vote of thanks.
All right, so we request Mr. Tejdeep Singh ji to kindly propose the thank you note today.
Yeah, thank you, ma'am. Thank you for
over to you.
inviting me for the vote of thanks.
Over to you.
First of all, thank you. Thank you, Kashyap sir, for giving such an insight in the resource estimation. But before that, I must thank you, MD sir, MD Ashok Kumar, for conceiving such a wonderful idea of water tech talk, in which the professors and teachers of your caliber can interact with the technocrats. Thanks sir for giving such a insight on resource estimation, which we are doing. As a scientist of Central Groundwater Board, I am doing from last 34 years, every second year and every third year, based on the GEC norms. Only I can know how complex these calculations are. So you have informed us, you have presented the calculations in such a manner that many confusions which we were having from last so many years are cleared now. Although we are using the Indian practice of GSC norms, the Indian practice, and the resource estimation, the importance of resource estimation can only be understood that on the basis of this resource estimation, we declare any district water stress or not. So all the government programs are based on these resource estimation only. On the basis of these resource estimation, we declared OE blocks, OE districts, overexploited districts, etc. One thing which you told during your deliberation is a forensic hydrogeology tool, which is an excellent idea because the camouflage polluted source which we when we go for the field works, it is very difficult. So there are many irresponsible people who are putting their effluent into the dry wells, which are in place polluting the groundwater resources. So once again, thank you very much, sir, for giving the insight on
Thank
the,
you.
on
Thank
the
you,
modeling and the
it is your initiative.
Kind participation.
We have known for long, and this
I thanks Water Digest team also for providing us a platform for giving the Water Tech Talk. And in last, I thanks the team NWM for facilitating us in for performing the Water Tech Talks and all the participants. Thank you very much for all the participants. Back to you, madam.
Thank you, Tejdeep Singh ji, and for all those who have joined us today through this platform as well as through social media handles. We are really glad that we could be a part of this wonderful initiative of National Water Mission. This is we started almost a year ago. This is the 10th Water Tech Talk, which was started along with Water Talk. So we are very happy that such initiatives are ongoing during pandemic, especially when we still have limitation of meeting and seeing each other physically. So we look forward to having all of you again with us on next Friday when we'll be hosting the Water Talk. Till then, please take care, and thank you so much, Dr. Kashyap, for joining us today for this Water Tech Talk.
Thank you.
Thank you so much, everyone. Thank you.
Thank you.